teachers have made it clear that if you take a, let's see, my chalk options, oh, wonderful. That if you take a state with a good semi-classical bulk description, and you consider the conformal field theory, and divide the conformal field theory into two pieces, which for the purposes of this talk will be called R and R bar, that in this context, the area of the corresponding bulk HRT surface describes the entanglement between the two parts of the CFT. Now, one might like to understand the more detailed form of this entanglement. And, you know, if you wanted to make a sort of naive first guess, a simple model for such entanglement might be that you would suppose that the entanglement is sort of all bell pairs that I will draw as lines connecting R and R bar. So you might imagine that there is a subspace of the Hilbert space on this side whose dimension happens to be e to the s, where s is the area of the bulk surface divided by 4. And you might imagine there's another subspace of R bar on the right whose dimension is also e to the s, and that the two subspaces are maximally entangled. So I'll make some cartoon of this kind to show this sort of simple model. Okay. Now, this is a simple model. For those of you that are tensor network fans, I'll mention that this is also effectively what happens in simple tensor network models. For example, if you study either the happy code or the random tensor network model of Hayden, Nizami, Chi, Walter, and Yang, then effectively you get an entanglement structure of this kind that matches this simple model. Now, as is well known, the full bulk story cannot be quite so simple. And this is easily seen by looking at consequences of this simple model. So in the simple model, the density matrix on one side takes the following form. It's just some constant, which normalizes things, multiplied by the identity operator in the appropriate subspace of the Hilbert space. All right? And therefore, if you compute powers of this, rho r to the n, it's just given by the appropriate power. And of course, the identity squares to itself. As a result, if you compute, say, a Renyi entropy, the Renyi entropy, Sn, is minus 1 over n minus 1, e to the minus, OK. If we take a trace of this object, I pick up another factor of e to the s from the size of the subspace. So I get an n minus 1 s, and I forgot my log, which is, of course, all important. And you see that when you take the log, you get an n minus 1, which cancels here. And so this is simply s. And so in particular, this model predicts that Renyi entropies are all constant in the sense of being independent of the Renyi number n, which is certainly not what one finds in an actual holographic bulk calculation. So this property is often called flatness of the Renyi spectrum, which would hold in this simple, or sorry, flatness of the Renyi entropies, which would hold in this simple model, but is again not a property of the full holographic system. All right. Now, there's been some discussion of how to remedy this problem, really over a number of years. And in particular, in the somewhat artificial case of pure 2+1 gravity without any extra bulk fields, in 2017, Han and Wang used what's called the Ponzano-Reggi model to argue that this problem can be solved by effectively summing over geometries. Now, this is not the place to go into the details of what those folks did, but let me just say that a generalization of that idea would be to note that, OK, up there the story was that the entanglement is described by the area of some bulk HRT surface. We should realize that the area of a surface should really be a quantum operator in the theory of quantum gravity because the geometry fluctuates. And so you might note that any quantum state of the kind we're talking about, where there's a good bulk description, should in principle be something that we could decompose as a sum of eigenstates of this HRT area operator. And you might suppose that while that simple model I wrote down might not be a correct model of the full state, you might suppose that a simple model of that kind actually holds whenever you're in an eigenstate of the HRT area operator, and that it is merely the fact that the full bulk state includes contributions from many such eigenstates that prevents the full bulk Renyi spectrum from being flat. Okay, so that's a next iteration on the simple model idea. The point of this talk is to argue that that is in fact exactly what happens in a gravitational system, and in particular in a holographic system, at least at leading order in the relevant large parameter, which is 1 over the bulk Newton's constant for all the holographers that are here. Okay. And as a small advertisement, I will mention that this structure, where for a given, if you will, eigenstate of the HRT area operator, we have this simple entanglement structure, but where there's a sum over such eigenstates, is effectively the entanglement structure of another class of tensor network models that a group of us introduced back in late 2016, which are called edge mode tensor networks. So that's just a small advertisement for edge mode tensor networks. Okay, so I will now proceed to my main argument. And I apologize to all the pure quantum information people here, because the rest of the talk is entirely discussion of gravitational path integrals. But that is as it may be. So I'd like to argue that, again, if we can somehow construct a state of RCFT whose bulk dual is effectively an eigenstate or a near eigenstate of this HRT area operator, then it has a simple entanglement structure. For simplicity, I'm going to assume that we're working in a context with some time reflection symmetry, so I can use the Ryu-Takanagi prescription instead of HRT. I'm going to also assume that the state is prepared by a Euclidean path integral, although we strongly believe that there should be a corresponding Lorentzian story using the Stringer-Keldysh formalism, but we haven't worked out all the details of that. Okay, so as I say, I'd like to construct a CFT state whose bulk dual has a given area for the HRT surface. Now, that's not something for which we have a direct recipe in the CFT. I know of no way to tell you a direct CFT construction that does that. On the other hand, what I can do, let's see. What I can do is to say, suppose we have a good CFT Euclidean path integral recipe to construct some state psi. Let's see, is that large enough? Is that large enough to read? Okay, to construct some state psi which has a good bulk dual. Then what we do know how to do is to translate that CFT path integral prescription into a bulk path integral to compute what you might call the bulk wave function. So for a given, say, metric on space in the bulk, we know how to compute that inner product by just translating the path integral into the bulk. Now, suppose I choose to compute this inner product, in particular on a bulk spatial slice that passes through the bulk HRT surface. So at least at the level, since I'm working at leading order in 1 over g Newton, I feel free to think a lot about classical solutions in discussing what I'm doing with the path integral. And in a path integral, in a classical solution, there's a unique HRT surface. And if you choose a slice of space, or a time slice, that runs through that surface, that amounts to basically a partial gauge fixing of your time slice, choosing a few of the coordinates. So I'm going to think about this as a partial gauge fixing of the path integral. And if you like, I can draw a little cartoon. This is a sort of 1+1 dimensional cartoon of the bulk, where what I'm doing is I have over here is maybe a piece of the boundary, and I'll call this R. Over here I have another piece of the boundary. I'll call this R bar. Somewhere in the middle, there is the HRT surface that I will call gamma R. And what I'm doing is just to consider some slice of the bulk, some moment of time in the bulk, if you will, that happens to pass through that HRT surface. And I am computing this matrix element defined by induced metrics H on that slice of the bulk geometry. Okay. So the point is that if you give me a path integral representation for a psi that has a good bulk dual, I can go and check which pieces of psi give me the area that I would like to specify on this HRT surface. Because after all, after I've done this gauge fixing, this area is just some combination of the degrees of freedom in the spatial metric on that slice. So the idea is then, let's pull this down. The idea is that if I want to prepare a state in which I have fixed the value of the area on this surface, what I should do is first prepare a more general state, compute all of its components from the bulk point of view, and then I'll just throw away the ones that give the wrong answer. Okay? In other words, through this procedure of basically discarding, did I spell that right? Yes, discard all of the h's where the area of gamma r does not equal some particular pre-specified chosen value a hat. If I just discard those components, it gives me a prescription for calculating the sort of bulk wave function of the state I obtain by taking my original state and acting with what's effectively a projection operator, where I project onto definite values of this HRT area. Okay. Of course, I have not computed the CFT wave function of this projected state. I've computed its bulk wave function, but that will be enough for my purposes. Okay. So what shall we do with this creature? Well, what I wanted to do is compute Renyi entropies, and I'd like to show that they are in fact flat in that sense of being independent of n. So let's start, and a natural place to start is with the first Renyi entropy. So first I should say Renyi of what? Of course, this is the state. We would now like to compute an associated density matrix. So I'm going to define a density matrix with a fixed value of the HRT area by thinking of this as the trace in the CFT Hilbert space. And what I'm going to do is, here I have this bulk representation that I'm able to compute. Because this is a duality, this projection operator must then have some representation in the CFT, even if I can't write it down explicitly. And so I'm going to use it here. In other words, I'm going to imagine that we reconstruct the HRT area using some operator on the boundary. And then I will project onto eigenstates of that operator. And for my own reasons of convenience, I'm going to choose to reconstruct this operator on R bar, the side I'm actually tracing over. So I'm going to write this as the projection onto the area gamma of R bar equals a hat. And because this is a projection, and because I'm tracing over R bar and the trace is cyclic, I don't need another projection on this side. Okay. Yeah?
Question to understand the notation. So a hat is a value, it's not an operator.
A hat is the value. Yeah.
So is why do you say eigenstates and not states with the expectation value of the area operator being a hat?
Well, let's see. It's a choice. That's what I want to do. And this prescription achieves that because I've thrown away all geometries in which it takes any different value. So there are no fluctuations of this operator left in this state. And we can coarse grain that a bit if you don't like an exact eigenstate, but that's fine. OK.
How coarse-grained is it?
How coarse-grained is it? Well, it's up to you. I mean, I only wish to do a calculation at leading order in 1 over g Newton for now. So anything which has a small width sort of compared to g Newton, or 1 over g Newton should be fine.
You phrase this as fixing the area operator.
Yes.
Since you're working to leading order in g Newton, should I think of it as fixing the entropy itself of R?
I need, in order to go through, how you think of it is up to you, but entropy, of course, is not a linear operator.
Well, that's the problem.
And I really want this to be a linear operator, okay, because of the procedure I'm going through. Now, it's true that at leading order in 1 over g Newton, we can often ignore the fact that entropy is not linear and there's some kind of equivalence, okay? But when it comes to a discussion of higher order effects, which I'm not talking about now, but I'd be happy to talk about later, the distinction is important, and I really do mean the area and not the entropy, okay? I really do. All right. So I'd like to calculate some Renyis, and let's start with the first one. First Renyi is just the trace, which is not 1 because my state is not normalized, especially after the projection. Instead, the trace is, of course, by construction, really the probability, this is a small p, the probability that the original state, psi, had area a hat for the HRT area operator. And of course, as is clear, this is given by simply summing over those geometries that are left, summing over those metrics such that the area does in fact satisfy my constraint. And then there's some psi, psi h psi. Now the point is that it's nice to think about this as a gravitational path integral. And which gravitational path integral is it? Well, okay, it's just the integral over all geometries, subject to the constraint that the area of this surface is fixed, e to the minus Euclidean action. And of course, as I said earlier, I have also done some partial gauge fixing to require the surface on which I originally computed the state to pass through the HRT surface. If I was having a discussion about higher order effects, I'd have to think about that gauge fixing, and maybe it would change the measure a bit. But at leading order in 1 over g Newton, it makes no difference, so I'm not going to worry about the details of the gauge fixing procedure.
So you're fixing the area and the extrinsic curvature at that point so that it is an HRT surface?
So I'm first of all fixing my bulk slice to run through the HRT surface. That's the partial gauge fixing. And then once I've done that, I am restricting the integral parametrics further so that at that surface with zero traced extrinsic curvature, I restrict the area as well.
When you do the path integral, you don't know that it will be an HRT surface. That depends on the answer for the path.
It does. And so this is an interesting subtlety that we can talk much more about later. For the purpose of this talk, I'd like to say that I just don't think that's relevant at leading order in 1 over g Newton. But I completely agree there are important issues there. What can be done is to talk about working with a surface with zero traced extrinsic curvature, and we can use that at least to some approximation as a gauge fixing condition. The hard part of the HRT construction is choosing the surface, the extremal surface with minimal area. Okay, and so in many contexts, I can choose to ignore that. I could choose to, for the purposes of this talk, or the purposes of many arguments, to simply say I'm going to work in a context where I assume there is a unique such extremal surface. I realize it's a tricky thing inside the path integral, but that's the approach I'm going to take for now. Okay. So yes, there are all these subtleties that I think are actually interesting, but I am going to at least boldly claim that they are not relevant for discussion at leading order in 1 over g Newton and proceed. Okay. If we do so, we can attempt to evaluate this path integral semi-classically. And it's fairly straightforward how to do that. The question is just how to implement that constraint. And of course, the simplest way to implement a constraint is often to add a Lagrange multiplier. So I will therefore rewrite this path integral as the integral dg, where I remove the constraint, e to the minus the Euclidean action, which here is just the bulk Einstein-Hilbert action, say. And then I will add a Lagrange multiplier term. So I will add an integral over a multiplier mu, I mu, and what does it multiply? It multiplies the area of gamma, I said r bar, minus a hat, like so. And what I wish to do, of course, is to approximate this by the action of some semi-classical solution. So there's some classical subscript c values of g and mu that make this stationary. I have chosen to write it this way, in part because on shell, one of the equations of motion is the one I get by varying mu, says that, of course, a hat equals a. That's the constraint I wish to enforce. So this part of the action, of the apparent action, does not contribute to the action of a stationary point. I get just this value. Raphael.
So you don't have in mind that you just have some HRT surface that has area A, right? You still want this to be inherited from this geometric state psi that you started with.
I'm not sure I understand the distinction. Perhaps we should.
What I'm trying to understand is whether away from the HRT surface that happens to have some area A, the geometry is, let's say, far away from it.
Yes.
It's expected to be as in the state psi that you started with.
Not necessarily. Not necessarily. So in fact, let me just say a few more words, and it will be clear that, that adding this constraint can affect the geometry far away, that this stationary point can be very different than it would have been if I didn't fix the area. Okay? So, great. So what is this? What do these things look like? Well, they are the values of the metric and this mu, which make the action stationary, make the action stationary. And as we just said, one of the conditions that it be stationary is that the area of the HRT surface equals a hat. Now, if I look at the metric equation of motion, the equation by varying the metric, well, OK, this is just a number, so the metric isn't involved. This is the area of some surface. And so once you know where the surface is, it's clear that this has the standard form of an action of what's often called a cosmic brane. Okay, it's just an object with some fixed tension mu that's been inserted into the space-time. Here it's a space-like codimension 2 brane. So the solutions, the stationary points for this problem are things that solve the classical Einstein equations away from the HRT surface. At the HRT surface, well, the effect of adding one of these branes with an effective tension mu is to induce some conical deficit or excess angle governed by mu. So it solves the normal equations away from the HRT surface, but on the would-be HRT surface, we are free to add a conical angle of our choice because we are varying mu. And we choose that conical excess or deficit in order to achieve the area we want. Okay. So the answer, Raphael, is that it's like adding a space-like cosmic string to a space-time, and that can change the geometry far away. Yeah?
But other than that, I would have thought that I could add all sorts of other matter content far away and still have HRT surfaces of area A in the middle. Is there something in the path integral that excludes that from contributing to the path integral?
Absolutely not. Whatever gives you a solution, and in principle, whichever one has the dominant value of the action is the one you'll keep.
But that doesn't really have a representation as starting with a particular global state psi and then projecting out. I mean,
We should perhaps discuss this later, but I don't think there's a simple way to construct this geometry in general, starting with the geometric representation of the global state psi. In fact, let me make the following comment. Okay, the geometry, the classical, the stationary point that would have described the original state psi is, of course, the one that would extremize this action if I first fixed mu equal to 0. Okay. Notice that that is exactly the same condition I get if I go back to this prescription for fixed values of the area, for fixed a hat, and I say, this is computing the probability that my original state had area a hat. Suppose I wish to find that value of a hat which had maximum probability in my original state. That would mean the value of a hat that makes p of a hat stationary. Taking a derivative here, you see that that sets mu equal to 0. Okay? So in other words, the geometry which is dual to the original state psi is also the geometry I can get from this fixed area path integral if I happen to choose a hat to be the area of the HRT surface in that original geometry. Okay? But if I choose a hat to be a different value, then in general I need to start from scratch, go solve the equations of motion, and see what happens. Okay. All right. So I should proceed before Alex tells me to stop. My goal was to calculate some Renyis. That was Renyi number 1. The more interesting things are, of course, the higher Renyis. So let's write down the formula for the Renyi entropy in order to keep track of things. This is a slightly non-standard way to write it down, but I find the signs hard to keep track of, and so it's easier for me if I simply say the Renyi entropy is the following. 1 over n minus 1 times the logarithm. And the complicating feature is that, as usual, we are dealing with density matrices that are not normalized. So I've absorbed what's usually a minus sign here to put the term that involves trace of rho to the n in the denominator, just so I don't lose it. And then there's the term that deals with the normalization, which is trace of rho a hat. And I need an nth power of that in order not to lose things. OK. So I wish to calculate this object. Thank you. And that looks like it goes there. Perfect. Great. And then if this hooks there, excellent. And it looks like if I was clever, nah, we'll just use the one that's been erased. That's fine. All right. So we wish to proceed. We want to compute this object, and I'll use this stick. OK, in doing the computation, the n minus 1 is easy. The numerator is the thing we've already just computed. It's over there. So all we have to do is figure out the denominator. What do we do with this rho to the n? All right. I'm going to give an argument for the answer based on drawing cartoons of CFT path integrals. Just to be definite, I will consider the case n equals 2, so I can draw a simpler picture than if it was arbitrary n, but the argument applies in general. So as a reminder, so these are CFT, this is a CFT cartoon, not a bulk picture. As a reminder, so far what we've done is to talk about the original density matrix. And we've computed this by using path integrals. So there is a path integral. I will draw it this way. I'll explain what I'm doing in a moment. There's a path integral that computes the original state psi. And there is, of course, a path integral that computes the adjoint psi dagger. And what we've done, of course, is to trace them by sewing these together over r bar. So this is r bar, like so. But we didn't just perform the usual trace. We also inserted an operator here, which was the projection described above. And I'll just call it P to avoid cluttering the blackboard. So that's our original density matrix rho. What we now wish to do is to compute rho squared. So I'll draw rho squared, r a hat squared. My drawings aren't very good, so I'm not going to try to draw well, I'll show you what I'll draw. I will draw simply 2 copies of what I have so far. And of course, we're going to sew them together to make the rho squared path integral. It is important that they have these projections P. So we sew these together. And I'm then free to think about this, after I sew these 2 things together, as a single geometry.
Why do you draw P is acting only on the left?
Because, OK, so it's some operator that was originally defined really in the bulk. I assumed in this story that I can reconstruct it as an operator in the CFT just on the side R bar. And that's why I drew it on the left. OK. That's in part for convenience, but it ties into a deeper story that we expect the relevant operator. In a few minutes, when I'll make some comments about operator algebra error correction, we expect the relevant operator to be reconstructible on both R and R bar independently. OK. So I've chosen to put it on the left. All right. So I can think about this as a single geometry in which I have introduced a conical excess here at the center. These are the open parts of my path integral. And so I've squashed this into a half circle, and I've squashed this into a half circle. And so there are now 2 projections P. OK. So the question is how to compute the trace of this thing. And so let's compute the trace. Of course, that means we're going to sew up this path integral. And I'd like to take this cartoon and rotate it 90 degrees. So I will draw the sewn object, trace of rho r a hat squared is this creature, where I have this conical excess in the center, and I have a projector there, and a projector there. And I will now cut this object apart to write it in this way. Like so, where I can, and I will take my conical excess. Sorry, this is also a half disk, indicating that I've taken my conical excess and divided it symmetrically between the 2 pieces. So my point is that this object, this trace, can now be thought of as computing the inner product of 2 states, each of which is a pure state defined on a certain geometry with a conical excess in it. OK? So, very good. So I want to think of this as defining a state in a CFT, which is essentially the CFT I started with. It might live on a slightly different geometry. OK? Now, there are some subtleties here. When you define a state using a path integral with a conical excess, it will have different high energy behavior at the excess than it would in a smooth geometry. So this is true. Okay. On the other hand, that's a localized ultraviolet issue here. And at the sort of formal level at which we've been having this discussion without regulators, and the formal level at which we can think of the CFT Hilbert space as being a product of a Hilbert space on the right and a Hilbert space on the left, it doesn't matter if you change the high energy behavior. You still live in that product. So I would like to claim that, at least morally speaking, this is again a state of the CFT living in a similar Hilbert space. And all we've done is apply the same projection operator that we already discussed. And we're doing it twice, one here and one here, and we are taking this inner product. So the point is that if it's the same projection operator we already discussed, we know how to compute its effects using the bulk path integral. That was this discussion we already had. So the claim is that this path integral has a bulk representation given by just the path integral I would have had without the projections, except that once again, I need to enforce constraints. And the constraints are fixing the area of the would-be HRT surface. I have two such constraints. I do that twice. But if they're both fixed to be the same value, then it's the same surface in the bulk. Having two such constraints doesn't do anything. I could remove either constraint and think about this as, in fact, having just one constraint, reducing this to exactly the kind of path integral I discussed earlier. Yeah?
There's something, maybe I lost this, but each of those halves that you're drawing
Yes.
could be under, well, they're actually like density matrices of the theory you start with, right?
The wonderful thing about the context with lots of time symmetry, not only of the state but of the theory, and the Euclidean path integrals that I'm using, is I can freely pass back and forth between density matrices on Hilbert spaces on one side and pure states on the two-sided thing. I have effectively an anti-linear time reversal operator in my pocket that allows me to do that.
That was my question, exactly.
Yeah. Very good. So I claim we know how to do this path integral in the bulk. And therefore, that the answer will be much the same. The answer will again be given by an expression of this kind, where the only difference is that now we have replica boundary conditions on the bulk path integral. OK. Good. So the point is now that in order to compare this trace with, say, that trace, the trace of the first power of rho, all we have to do is understand how the semi-classical stationary points are related. And the point is that because of this recipe of introducing a cosmic brane and allowing yourself to tune the tension and thus tune the conical deficit or excess in order to get the right area, it is easy to construct this bulk saddle for this path integral if you already have the bulk saddle for the first path integral. And in fact, this turns out to be just the construction that Fursayev used some years ago in an attempt to derive the RT formula. So these are sort of Fursayev geometries. So to say that in more detail, the point is that what do we have here? The boundary conditions. So let me now pass to a bulk cartoon. In a corresponding bulk cartoon, the boundary conditions on this path integral are just two copies of the boundary conditions on the n equals 1 path integral. Have I written that in any place? Here, right. All of that circle got squeezed into a half circle here, and then again here. So as far as a bulk Euclidean solution, if I simply take two copies of the bulk solution from this, cut them open along some surface that connects the boundary to the HRT surface, again squash them into half a space, and glue those two things together with a 2 pi conical excess in the bulk, I will satisfy these boundary conditions. And if my original bulk saddle had the correct area, A hat, on the HRT surface, then when I stick the two geometries together, they will again satisfy the constraint here. Okay. If you'd like to look at a picture, instead of taking time to redraw things, I will simply note that you can go back and reinterpret my CFT cartoons as bulk cartoons, where the middle is now the HRT surface, and you see how this all works. So it turns out that immediately gives the desired result. Since my time is up, I'll give you the short version of the argument as opposed to the long, detailed computation. I thought you might enjoy the long, direct calculation, but Alex will cut me off before I get there. So let me just give you the short version of the argument. The short version of the argument is to think about the normalized versions of these density matrices, of these powers. So consider a normalized rho tilde r a hat, which is just rho n r a hat divided by its own trace, whatever that may be. And the point is that I've actually just argued that this squared density matrix could be thought of as a density matrix itself for a CFT state on some slightly singular geometry. And as a result, it makes sense to talk about the von Neumann entropy of this normalized version of the power density matrix, of the replica density matrix. And what is this going to be? Well, we know that the von Neumann entropy in the CFT is described by the area of the bulk HRT surface. So it's again just fixed by this parameter a hat. So this is precisely a hat over 4 g Newton, independent of whatever is the Renyi number n. So these are quantities which the name keeps changing slightly in the literature, but we've chosen to call them refined Renyi entropies. And you'll see that these quantities are immediately independent of the Renyi number n. A little bit of algebra then shows that the original Renyis are also independent of n as well. And so the Renyi entropies of our fixed area states will be flat, independent of n, at least at this leading order in 1 over g Newton. Okay. Yes, please. I think that's true. The rest of it could have been done for any surface. I have to think back. I did have a preference for choosing. So the only other issue, of course, is if you have the area of some more general surface, which you might suppose lies either in one entanglement wedge or the other, then that area will certainly not be reconstructible on both sides. But modulo that caveat, that's the only thing which has been particularly important here, I agree. Okay. But that's, of course, what we care about. We're trying to study quantities related to entropy, and those know that you have the HRT surface as opposed to a different surface. All right. So Alex is going to cut me off in just a moment. So I guess what are my remaining comments? My remaining comments are that, again, for tensor network fans, I think this is a great place to advertise looking back at our edge mode tensor networks. It looks to me like they have enough, this is the same structure that they have, and it looks to me like there's enough room in the edge mode tensor network construction to reproduce Renyi entropies associated with any bulk quantum gravity wave function, and therefore in particular the things we find in holography, but that remains to be verified, and it'd be good to investigate that. I will also mention, although I don't have time to talk about the details right now, that one of the reasons this entire story is interesting is the idea that we could somehow work to higher orders and study things, well, and find something like a flatness at higher orders in g Newton. Of course, we know, well, let me just say that that's kind of interesting, and it turns out to be deeply related to questions about modular flow and exactly how well one can use modular flow to reconstruct bulk operators using the boundary, using the prescription from Faulkner and Lefkowitz. So that's all about future work, and thank you for listening.